Hey, Honors Pre-Calc, welcome to lesson 1.6, inverses and variation. This is the last lesson in Unit 1. So after this lesson, you'll still have a lesson 6 assignment to do, and then we will have a review and have a quiz in class. So here's what we're doing for our last lesson today. What we are going to do: you will find inverse functions algebraically. We will verify two functions are inverses using composition of functions, which you may remember from last lesson. That means, for example, f of g of x. That's a composition of functions. And students will determine graphically if a function has an inverse. So we'll take a look at graphs and what graphs of inverse functions look like. The essential question today is, how do you find the inverse relation of a function and determine if it is a one-to-one function? So that gives you a preview of some vocab that we're going to be looking at as well. All right, so I'm going to switch over to the notes now. All right, here we go. So we're looking at, again, lesson 1.6, inverses and variation. And this is really two different topics, right? We're going to look at function inverses, and then we're going to look at variations separately. Variation is usually within one equation or one function, and inverses are when you're looking at two functions and comparing them. So first of all, we have this thing called the identity function, which is f of x equals x. That's a straight line, right? So if we drew the coordinate plane here, it would look like this. It would go through the origin with the slope of 1. And that's going to be important for inverses. The next thing is this word IFF, or this abbreviation. And IFF stands for if and only if, right? And so that is an abbreviation that you see in a lot of higher level math theorems. You may remember that phrase from geometry within proofs. I'm not sure if you used it, but I feel like it is likely that it would come up there in some aspect, and I'll show you what it means. I'll tell you what it means, actually. If and only if is like a part of an if-then statement when the reverse is also true. So, for example, let's say that you have my class for first period, and first period happens every day, okay? So this could be a statement like, you are in Mr. Bigelow's classroom if and only if it is period 1. And what that would mean is that both ways this statement is true. If you're in Mr. Bigelow's classroom, then it's first period. And if it's first period, then you're in Mr. Bigelow's classroom. That's not necessarily a perfect example, because you could definitely come to my room later in the day and it wouldn't mean it's first period. But let's say that I live in a house by myself and no one ever comes over to visit me, okay? This is purely hypothetical. So in that case, if someone is sitting in this chair that I'm sitting in right now, then it's Mr. Bigelow. That one doesn't really work, does it? I'm thinking through this in my head. If someone's sitting in this chair, then it's Mr. Bigelow. But then backwards, that would mean if it's Mr. Bigelow, then he's sitting in the chair. And I'm not always sitting in this chair. There's got to be a better one. I don't know. Let me know if you think of something. It's a if-then statement where the reverse is also true. I liked that first one that I said, but we'll keep going. I'm not trying to waste your time here. So an inverse function switches the x and y coordinates of a given function. It's denoted as f to the -1 of x. That's generally known as an inverse notation. So f of x and f inverse of x are inverses if and only if f of f inverse equals x and f inverse of f equals x. So that's where that IFF comes into play, right? That if and only if. So that means this goes both ways. It's if this, then this, and if this, then this. Both of those ways are true, and we're going to see that when we get to example 1 in a second. When we graph inverses, If a comma b lies on the graph of f of x, then b comma a lies on the graph of the inverse. So that the coordinates switch. So xy switches to yx. And that's different from, the symmetry that we were talking about before. That always changed the sign of a, b, or both. This actually switches the coordinates, switches the x's with the y's. And the graph of the inverse is a reflection of the graph of f over the line y equals x, which is that identity function that we were just talking about at the beginning up here. So we're going to take a look at the graph of that in a couple minutes. One-to-one function is if a function passes both the vertical line test and the horizontal line test, then no y value is matched with more than one x value, and this is one-to-one. We'll look more at that in a little bit, and hopefully it'll make more sense. A function f has an inverse that is a function if and only if f is one-to-one. So there's another if and only if statement. And then that brings us to our variation. I am going to fill this in for you now, just so I don't forget later. But we'll talk more about this when we get to variation towards the end of the notes. So first of all, we're going to use the letter K to represent our constant of variation. Some textbooks and some teachers use A or N. So if you've learned about variation before, you may have used a different letter, but we're going to use K. That means the same thing. So direct variation always shows up as y equals kx, and it means y is directly proportional to x. If we have a variation to a power, it would be like this. If we have inverse variation, it would be y equals k over x. And if we have joint variation, it's got more than two variables, more than just x and y. So something like this. Usually there's just one lone variable on the left, and then there's a whole bunch of things multiplied or divided on the right. We'll see some examples of that. All right, let's take a look at example 1 here. We're going back to inverses for now. So find the inverse function of f of x equals 4x. So first we're going to do that. So we're going to start with f of x equals 4x, and the first thing we're going to do is rewrite this with y instead of f of x. It means the same thing, right? That's just function notation. This is our standard notation. And to create the inverse, which we're going to do in this next step, we swap the x and y. So we're going to end up with x equals 4 times y. And normally what we do next is we solve for y. So imagine that we're going to divide 4 on both sides. So it's going to become 1/4 x equals y. And the last thing that I would like us to do is just write this using the function inverse notation. So instead of y equals, it's going to be f to the negative 1 of x equals, and it's that same function, 1/4 of x. Or x over 4 means the same thing. So that's our inverse. But now what we're going to do is verify that both this composition of functions and this are equal to the identity function. Remember, the identity function is f of x equals x. So that function's showing up multiple times in our lesson because we're going to look at it when we look at the graph, but it's also right here. It's the composition of functions have to equal x, which is our identity function. It's kind of like when you multiply two multiplicative inverses, like 1/4 times 4, you get 1. When you add two inverse numbers or additive inverses, you get what, like 5 plus -5, and you get 0. So 0 is the additive identity. X is the inverse identity for functions. So anyway, let's keep going. So we're going to try to find f of f inverse and f inverse of f. So f of f inverse. So as usual, just like we did last lesson, we're going to start on the inside and work our way out. So the f inverse is 1/4 x. And now we're going to plug that into the outer function, which was f of x. So that's right here, that's 4x. So we're going to do 4 times 1/4 x. And 4 times 1/4 x, the 4 times 1/4 is 1, so we get x. So that worked. Check. Now we're going to try the other way around. So we do f inverse of 4x. So we're plugging 4x in for x in the inverse version. So we have 1/4 times x, which is now 4x. And again, that simplifies to x. All right, so it worked. So we've verified that both versions of the compositional functions are equal to the identity function. Therefore, these are 100% inverses. Definitely worked. This is the inverse of this. Let's keep going. Example 2. Which of the following functions is the inverse of f of x equals 5 over x minus 2? So there's multiple ways that we could do this. There's 2 options here. This is multiple choice. I think the easiest way is going to be that first way that we did example 1. So we changed f of x to y. And we're just going to switch the x and the y. So we get x equals 5 over y minus 2. Now we try to solve for y. So I'm going to multiply the y minus 2 to the other side. And I don't really want to distribute this x because that's going to make it messy. We could. Maybe I'll show that over here, but I'm just going to divide x to the other side right now so I don't have to deal with it. So we have y minus 2 equals 5 over x. And then we add 2 and get y equals 5 over x plus 2. So that's definitely this function that's called b of x over here on the left. So there, we solved it. Now let's say we got to this step, and alternatively, instead of just dividing by x, we distributed the x. So we have xy minus 2x equals 5. Again, that's just another way of writing this equation. And let's say we did that, and now we're going to try to solve this for y equals. So you probably would also add the 2x to the other side, and then divide by x. And now we have y equals 5 plus 2x over x. Now that's not either of these answers. So that might be a little confusing, but what I would do is just distribute this denominator. So we have 5 over x plus 2x over x, and then those x's cancel. And then right away we have the same answer. Okay, so that's how we're going to do that one. Okay, so that is the answer for example 2. Let's keep going. Now we're going to look at the graph. So we're going to sketch the graph of the inverse functions below on the same coordinate system and show that the graphs are reflections over the line y equals x. So we have symmetry this time, but our symmetry is with the line y equals x. I'm going to try to use some different colors here. So y equals x is the line right here. All right, and what we're going to be doing is graphing each of these functions. So f of x equals 2x minus 3. I'm going to do that in purple. And hopefully you can tell the difference between these colors on this camera. So let's just try plugging into values and see what we get. Well, it's a line. We can just sketch it like a line. So we have a y-intercept of -3. And our slope is 2. So we can go up 2 over 1. And I'll connect the dots. Okay, and then the other one I'll do in orange. And this one is, I'm going to distribute the 1/2 so that it's more like a line. Okay, so we have a y-intercept of 3/2, which is 1.5. And then we go up 1, right 2, up 1, right 2. That's kind of weird because we're like halfway between 2 points, but it still works. Okay, and if you take a look at this, you will see that if you kind of slant your head a little bit, it looks like those are exact mirrors of each other about that dotted line, right? And that's what's going to happen every time that you have an inverse. It flips over that line. And we can think about how the ordered pairs switch. So we have a point right here at 1, -1. If we switch that ordered pair, it becomes -1, 1, right? Instead of 1, -1, it becomes -1, 1. So if we go to -1, 1, we end up here. And that's on the other line. So it works, right? You can do that for any ordered pair. You can switch the x and the y and it will work. All right, we're going to move on to example 4, but I can tell that my screen is lagging a little bit, so I'm going to pause for a second, try to fix it, and then come back. All right, we should be good now, so let's keep going. We're moving on to example 4. One-to-one functions. Determine if each function has an inverse that is a function using the horizontal line test. So here's what we mean by this. X cubed minus 1, this graph is here. Does it pass the vertical line test? Yes, definitely. I can drag my vertical line across this graph, and it only touches at most once. It only touches at most once at a time, right? If I do the horizontal line test, it's the same exact style test, but we check it with a horizontal line. Now this one looks a little bit funky right here, but it does pass. It's never actually just a horizontal line right here. So it doesn't touch more than once. So this one does pass. So does it pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. In other words, this is 1-to-1. It is, the inverse is a function. And the original is a function. So inverse is a function. So in other words, this is 1-to-1. A 1-to-1 function means that the function and its inverse are functions. Now, how do we know this? So think about this. The horizontal line test works because if we go back and look up at this graph, if we switch a function across this dotted line, which is what an inverse is, all of the vertical line test results become horizontal line test results, right? The x's and the y's switch. So if you had a vertical line test that worked, now you have a horizontal line test that works, and vice versa. If the vertical line test worked, and then you switch to the inverse, now the vertical line test works. So if we know the horizontal line test of this function works, that means its inverse is a function because the inverse will pass the vertical line test. We're going to do the same thing for letter B. We're checking the vertical line test, and we'll check the horizontal line test. So is this a function? Does it pass the vertical line test? Yes. So this is a function. Does it pass the horizontal line test? No. Right? You can check anywhere. Any of these lines up here will not work. It touches more than once. So, and that's the horizontal line test. So we know the inverse is not a function. All right. Hopefully that makes sense for you. If we flipped this, it would be sideways like this. And you can tell already that that would not pass the vertical line test. So indeed, the inverse is not a function. All right, let's keep going. Example 5, finding inverse functions algebraically. Find the inverse of each function algebraically. Now, that's kind of already what we've been doing, right? Algebraically means that we just switch the x and the y manually and then solve for the new y. So that's what we're going to do. We start with y equals 5 minus 3x over 2. We make this x equals 5 minus 3y over 2. Now we're going to solve for y. So I'm going to multiply by 2. And subtract 5. And then divide by -3. So we end up with y equals 2x minus 5 all over -3. Or you could write it as -2/3 x plus 5/3. I would also probably recommend that you write this in function inverse notation. So it looks like this. but that's the same thing. All right, let's check the other one. Y equals the square root of 2x minus 3. The inverse is going to switch the x and the y. And now we're going to have to solve for y. So we square both sides. We add 3. And we divide by 2. So we get 1/2 x squared plus 3/2 equals y. So our inverse, whoa. Let me rewrite that. Our inverse is 1/2 x squared plus 3/2. All right, now if we look at these graphs of the original and the inverse, it should flip over the line y equals x. We know that. So let's take a look. So there's our original. Here's our new one. Okay, and I'm also going to make a y3, which is going to be just y equals x, so we can look at the identity line that we're supposed to be flipping over. All right, now I see an issue. I don't know about you, but take a look. This blue curve, which is the one down here, if we think about flipping over this line, it flips to this, right? But this whole section over here would flip down here, and it's not there. It's missing. And that I just drew on the screen, so that's awesome. That means that we have to restrict our domain. So if we check the graph, the red curve doesn't exist over here, or it shouldn't, so that it actually matches up with the blue curve. So what we're going to do is we're going to say the domain is going to be from 0 to infinity. Now, how can we predict that that's going to happen? Well, it has to do with that we just squared both sides here, because if we think about this square root wasn't plus or minus in front, it's just positive. But once we square it, now this x could have been positive or negative. It doesn't matter because it's squared, so it's canceling it out. So we introduced a whole bunch of new solutions in from this step to this step. If this had started with plus or minus here, then this would have been the domain. But now, because of this sticky situation that we're in, we have this issue. So whenever you have squared or square root in a function that you are finding the inverse of algebraically, what I would recommend is that you take a look at the graph and see, do we need to restrict the domain so that it actually matches up? And if I tilt this sideways, it becomes more obvious that I'm supposed to be symmetrical about this line. I have this part, and then right there, this part is missing over here. So how do I get rid of that part in my solution? I say that for this curve, which is red, which I know is hard to see in the recording, we only want the domain from 0 to infinity, so that this part to the left is just gone. And now it'll be correct, okay? So I hope that's not too confusing. It won't come up that often, but if it does, you should look at the graph always to see if your functions really do reflect over that line y equals x. Example 6, direct variation. In Pennsylvania, the state income tax is directly proportional to gross income. You are working in Pennsylvania and your state income tax deduction is $46.05 for a gross monthly income of $1,500. Find a mathematical model that gives Pennsylvania state income tax in terms of the gross income. All right, so for this question, we've completely switched gears. We're done talking about inverses now, and now we're going to be talking about variation. So we have this idea of direct variation. The key here is that because we were told that this is directly proportional, that's how we know that this is direct variation. And this first sentence is telling us how to set up our equation. The equation for direct variation is y equals kx. That's from the first page of the notes. And y is going to be the state income tax. And x is going to be the gross income. I always think of it as we're reading across this equation the same way we read across this sentence. The state income tax is directly proportional to the gross income. So Y was the first phrase written here. It's the state income tax. Is the equals. Directly proportional is the K. To the gross income is the X. So that's why I labeled the Y and the X the way that I did. Again, so now we have a state income tax deduction. So our Y is going to be 46.05. And our gross monthly income is going to be 1,500. Find the mathematical model. So we have a sample Y and X. We're going to use that to find K, our proportionality constant here. So we have 46.05 equals K times 1,500. I'm going to divide both sides by 1,500. And we get 0.0307 is K. So if I plug that into the original, just like it was a slope, we would get Y equals 0.0307x. And that's our model. The question said to find the model. So we did it. Boom, that's the model, we're done. Let's keep going. The distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. So this time we're going to have the equation Y equals kx squared. It's directly proportional, so it's Y equals kx, to the square of the time it rolls. So it's telling us that we're taking the x and squaring it. Just like last time, we're going to read this sentence to figure out what Y and X are. The distance the ball rolls is, so Y is going to be the distance, directly proportional to the square of the time. So X is going to be the time. During the first second, the ball rolls 8 feet. So now we're getting our instant scenario that we're going to use to plug X and Y in to find K. So in this scenario, during the first second, so X is 1 second, the ball rolls 8 feet. So the distance is 8 feet. So let's plug that in and find K. So Y is 8, so we have 8 equals K times 1 squared. Not too hard of an equation to solve. We get that 8 is K. So our equation is going to be Y equals 8x squared. We plug the K in, we pull out the X and the Y. And now we're going to use that equation that we just found to figure out how far will the ball roll in 3 seconds. So again, 3 seconds is the time, so that's X. So if we have Y equals 8x squared, we're plugging in 3 for X. 3 squared is 9. So 8 times 9 is 72, and that's in feet, just like it was in part A. And there we go. So the ball is rolling a lot faster now than it was after 1 second, but that's how gravity works, right? We've got acceleration in the mix. So that is the beginning of direct variation to a power, right? Next up, we're going to talk about inverse variation. Inverse variation typically has the formula Y equals K over X. That's on the front page of your notes. Direct has Kx, inverse has K over X, and inverse variation always has a kind of a downward slope over time, or as X gets bigger, the Y gets smaller. You think about this as your X and your Y axis. If we were looking at direct on a graph, it would look like this, something with a positive slope. As X gets larger, Y also gets larger. So for inverse, as X gets larger, Y gets smaller. And so let's take a look at this inverse variation question. And gas law states that the volume of an enclosed gas varies directly as the temperature and varies inversely as the pressure. Now I want to kind of expand on this because I think it's a little bit unclear that that's describing what we're going to call joint variation. In other words, both of those things are true at the same time or in the same equation. The pressure of a gas is blah, 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 when the temperature is blah, and the volume is blah. Okay, write an equation relating the pressure, temperature, and volume. So gas law states that the volume of enclosed gas, and I'm actually going to use different variables here. We're going to use pressure, temperature, and volume, PT and V. So the volume of the enclosed gas is directly proportional to the temperature. So we're told that it varies directly as the temperature, so KT, and inversely as the pressure at the same time. So in the same equation, it's inversely proportional to the pressure. We don't add in another K or an extra constant of proportionality, constant of variation. Instead, we just kind of multiply or divide more things. So it's inversely proportional to the pressure at the same time. So we're going to have the direct part in the numerator and the inverse part in the denominator. The K stays in the numerator. So our volume equals K times temperature divided by pressure. Again, the volume varies directly as the temperature and inversely with the pressure at the same time. So that's how this gets set up. Now we have all these sample numbers to plug in so we can find K. So the volume is given as 8,000. The T is the temperature given to be 294 Kelvin. And the pressure is 0.75. So we're going to multiply and divide to get K. So we'll multiply the 0.75 to the other side. And then we'll divide by 294. And I got a K of 1,000 over 49, which you could also write as a decimal, but I think it would be rounded. So it's going to be better this way. Let me just show you how to do that in case you forget on your calculator. So if you're using one of these TI-83, TI-84s, I'm going to start with this 8,000. And I'm going to multiply by the 0.75 to get that to the other side. And then I'm going to divide by 294 to solve for K. We get 20.408, blah, blah, blah. I'm going to press math 1, enter, to change it into a fraction, 1,000 over 49. And that's now exact, whereas if I had to round a decimal, it would be an estimate, but it wouldn't be an exact answer, right? So we have 1,000 over 49. So now we have, if we plug that back in over here, we have V equals 1,000 over 49 times T over P. I think a nicer way to write this would actually be V equals 1,000 over 49 times T over P. It means the same thing, it's just not a fraction inside of a fraction. So I like it that way. It's up to you. Either way is fine. Even if you're on the decimal, that's fine because the question didn't specify. Letter B though, find the pressure when the temperature is 300 Kelvin. The volume is 7,000 centimeters cubed. So find the pressure. So the volume is 7,000 now. We're going to use the same model that we just created in letter A. Temperature is 300. We don't have a P. So we're going to have to solve for P. So what should we do? We could multiply these fractions together. We end up with 7,000 equals 300,000 over 49p. I just counted up the zeros and made sure we had the same number. I'm going to multiply 49p to the other side, and we get 343,000p equals 300,000. And then I divide the 343,000 to the other side, and I get P equals 0.875. And we use the same units from part A, which was kilograms per centimeter squared. There we go. Last question, another example of joint variation. The simple interest for a certain savings account is jointly proportional to the time and the principal. Okay, so in this question, I'm going to make interest I, principal P, and time T. And the simple interest is the first phrase. So simple interest is, so I have I equals, it's jointly proportional to the time and the principal. Now, jointly proportional, if we don't have a specific reference to direct or inverse variation, jointly proportional means direct, and we would multiply everything. So it's jointly proportional to the time and the principal. So it's going to be K T P. It's jointly proportional to the time and the principal. We multiply everything together. If it said anything about inverse being in this mix, then we would divide by that part. But it didn't. We assume everything is direct. We multiply it together like this. So we have our equation. Again, we have after 1 quarter, the interest on a principal of $5,000 is $43.75. And what we need to know, this says after 1 quarter. So you might be thinking, what does that mean? And I want you to write this down, for interest problems. If I could spell. For interest problems, time is always measured in years. So when we think about what we're going to plug in for time here, after 1 quarter means after a quarter of a year already. So we're actually going to be plugging in 1/4. So our I is 43.75. K is what we don't know. The T is 1/4. And the P, the principal, is 5,000. That's all given in the second sentence up here. And now we're going to solve for K. I have 43.75 equals 1,250K. Divide by 1,250, and we get K equals 0.035. So our final answer is I equals 0.035 TP. Letter B, find the interest after 3 quarters. So this doesn't give us a new scenario. This is still part of the same scenario. So we still have the same principal amount. We're talking about a savings account. So principal amount is what you start with, what you are putting into the account at the beginning. So we're plugging in $5,000 into this account. And after 1 quarter, we're making $43.75. That is an amazing deal. You should definitely do that if you have this type of interest rate. I like it. But let's talk about after 3 quarters. So we're going to use the same model. I equals 0.035 TP. We're plugging in 3/4 now for T. We have the same principal of 5,000. And we're trying to find the interest. So we're trying to find the I. So we multiply these things together and round to $131.25. Okay, so that's how we do that. That's the end of the notes. So we learned about inverses and we learned about variation. Again, this is the last lesson in Unit 6, so we'll have a review next. But I hope that you understood this, and please let me know if you have any questions. Thank you very much for watching.